Hello, my name is Jack Wetherell, and today I'll be speaking about work done by myself and my collaborators on using different formulations of quantum mechanics to answer some given problems about molecules. So first, what are the general overarching aims of our group? First, we wish to accurately describe the flow of electrons through molecular junctions. So if we take this molecule on the right and you were to apply a large electric field across it, what would the current be? How would the electrons respond? What would be the transmission and reflection coefficients, etc.? Second is to accurately describe the structure of molecules. And the third is to accurately predict the excitation properties of molecules, such as the energy to add an electron, remove an electron, and so on. Today we'll be mainly focusing on the second problem as an example, to accurately describe the structure of the molecule. So, why can't we just solve this directly? Well, the problem is our system is a system of interacting electrons, where there are many electrons that each independently feel the external potential. This is the potential due to the nuclei in the system, which we consider fixed within the Born-Oppenheimer approximation, and also the electron-electron interactions. Now, it is this second term that is very difficult because each electron interacts with every other electron, meaning that for systems with more than 2 or 3 electrons, this becomes impossible to solve computationally. In principle, we should simply construct the many-body Hamiltonian to be the kinetic energy plus the external potential and electron-electron interactions, and from this solve the time-independent Schrödinger equation to give us the ground state many-body wave function of this system that depends on the positions of every electron. And in principle, from this quantity, we can extract any observable we'd like from the system. But the problem is solving the Schrödinger equation for a system this complicated is impossible. So what do we do instead? Well, the first method is to reformulate your theory of quantum mechanics, so it is in principle the same theory and is exact, but it is much easier to approximate and therefore, for more and more computational effort, get closer to the right answer without having to solve the whole problem in one go. The first of these is many-body perturbation theory. And how this works is if we consider our molecule here, and then we can illustrate the charge density. So a region mod blue says there is more likely to be an electron found, and a region mod black shows there is much less likely for an electron to be found. So for this molecule, the electron density would look something like this. Now, many-body perturbation theory asks the question, if we add an electron to the system at position x and time t, and later look to remove an electron at time t prime, what is the chance that in this time the electron has propagated from position x to position x prime? That is to say, what is the probability that an electron added to the system at position x time t ends up later at time t prime at position x prime? Now, the quantity of interest in many-body perturbation theory is called the many-body Green's function g, and it depends on x, x prime, and the difference in times. Now, the reason it depends on the difference in times is because we're assuming our system starts in a relaxed state. There are no external fields on it or anything like that. Therefore, it only matters the difference between the addition and removal. If we want to calculate the probability of an electron propagating from x to x prime, the probability is the modulus squared of g, and that is why g is called a probability amplitude. In principle, if t prime and t are the negative sign, so t prime comes before t, this can be considered as removing an electron and then re-adding it. So g considers the propagation of both electrons and holes through the system. Now, how do we calculate this quantity g? Well, we use Feynman's theorem that tells us the total probability amplitude an event is the sum of the probability amplitudes of all the possible ways it can happen. So we can do it with our simple toy model here directly. So the first way it can happen is we add an electron and then it propagates through the system without interacting, and then we remove it. This is called the non-interacting method, and the Feynman diagram corresponding to this event is shown on the right, which an electron simply propagates from spacetime point 1 to spacetime point 2 with no additional events happening, and this is a very trivial non-interacting approximation. So we can add that diagram to our list of ways this event can happen, and then we can look at a more complicated case, where an electron is added, and as it propagates through the system, before it's removed, it interacts via the Coulomb interaction with an electron density already in the system. So the region of density circled here. It feels an interaction and then propagates through the rest of the system and is removed. The Feynman diagram causing this event is shown on the right, where the electron propagates from region 1 to region 2, where on the way it feels a Coulomb interaction with the charge density. The reason the charge density is shown with a little circular arrow is because this is equivalent to us counting the number of electrons at that point, and hence removing an electron, counting how many there are, and putting it back. And this is called the Hartree approximation. And this is better than our non-interacting approximation, but it still has a long way to go. And the main reason is that in reality, electrons are indistinguishable particles. And if we just include these two diagrams, we are saying they are distinguishable. Because we are saying when we add an electron, when we later go to remove an electron, we know that it was the same electron that we added. Whereas in reality, this isn't true. The electron that you receive at point 2 can really be an electron that was already in the system, and hence an electron that was knocked out of the system due to our added particle. So if we want to treat our electrons as indistinguishable, we should include a diagram that takes account of this effect. So we can do that, and so we add an electron, it propagates through the system, and then due to the Coulomb interaction, it knocks an electron already in the system out, and that is the one we see. This leaves an electron and hole in the system, but this we cannot end here, because our system has to end up with only electron being found at x prime t prime, not other electrons and holes being found in the system. So our electron fills in the hole, and then we remove our electron from position x prime t prime. The Feynman diagram corresponding to this event is shown on the right, where an electron enters the system and propagates through, and then due to the Coulomb interaction, knocks an electron already in the system out, and our added electron then fills in the hole left behind. Our electrons are now treated as indistinguishable and therefore obey the Pauli principle, so now including these three diagrams gives us the Hartree-Fock approximation. So what are we missing now? Well, there are lots more events we are missing, but most importantly, the system is not responding to the addition of our electron. In reality, if you injected an electron into the system, the other electrons would screen the addition or move out of the way of the electron and become excited by this sudden hit of charge to the system. And we haven't included any of those. So one such way this can happen is you add an electron to the system, it propagates through, and the Coulomb interaction causes an electron in the system to become excited out of its ground state, leaving a hole behind. Now this electron, and hole all propagate through the system until eventually the electron and hole recombine, and then this, in turn, affects the trajectory of our added electron. The Feynman diagram corresponding to this event is shown on the right, where an electron propagates through the system, and along the way, due to the Coulomb interaction, an electron already present in the system becomes driven out of its excited state and moves out of the way of the electron, leaving a hole behind, and this event adjusts the probability of an electron propagating through the system. If you include diagrams of this type, you get the GW approximation, which can be thought of as screened Hartree-Fock, where you add the screening effect due to the Coulomb interaction to your Hartree-Fock picture. Now in principle, you can also include every combination of the diagrams I've shown, so one Hartree, one exchange, two Hartrees, two exchange, and so on. But even after you do that, there are still many, many more diagrams, such as an interaction between the electron and hole pair created, and so on. So let's write this a little bit more mathematically. So we say that our G, our Green's function, the probability amplitude of the electron propagating from position xt to spacetime position x prime t prime, is the first term is G0, the non-interacting Green's function, where it propagates without interacting, plus it interacting once via a potential which we'll call sigma, the self-energy, then plus 2 interactions, plus 3 interactions, and so on. You can rearrange this equation, and this is called the Dyson equation, where you now must approximate the self-energy sigma. And now this has achieved our aim. We now have a formulation of quantum mechanics where we have, in principle, an exact answer with just one part we can approximate, and we can keep adding more and more advanced approximations to this that we're willing to calculate to get much better and better answers. And so we can show this is equivalent to our picture before, because the self-energy is split into three parts. The Hartree potential, which is the classical Coulomb interaction between the particles. The exchange potential, that must be included for our systems to obey the Pauli principle, as in reality the electron we receive may not have been the electron we added, so this takes account of electrons knocking other electrons out of the system. This is called the exchange interaction, and plus the correlation part. Now the correlation is the fact that our added electron causes the electrons in the system to respond, and hence the motion of our added electron is correlated with the motion of the electrons in the system. So if we include none of these terms, we just get the non-interacting diagram. If we just include the Hartree potential, we get our Hartree diagram. If we include the exact exchange potential, we add the exchange diagram, and of course all possible combinations of these diagrams. If we then add the correlation potential due to non-interacting electron hole pairs, which for historical reasons is called the random phase approximation, we get diagrams of this type. We can then, for example, add electron hole interactions, which would give us what's called the 2-point Beta-Salpeter equation, and this would add more diagrams, and so on. So we have turned our impossible to solve Schrödinger equation into a solvable set of equations that where we can slowly add more physical events and slowly improve our approximation. That was option 1. There is a second option, a different formulation of quantum mechanics that also has this feature of improved approximation. And this second method is called density functional theory. Now this is a very different approximation where it is tied to the electron density. And this theory tells you, imagine somehow you've been given the exact electron density of your system. Well, Holmberg and Cohen proved if this is the case, you can show that there is a one-to-one mapping between the density, the external potential, the wave function, and the total energy. Therefore, if you have the density, in principle, you know every observable of your system, because from the density you can get the wave function, and as we said previously, from the wave function you can get any observable O. Therefore, if you're given the ground state density of your system, you can predict any observable of the system by going via the wave function. This theory is then now exact, because if we are given the exact density and we have an exact functional, we can get any property we want. But the problem is, this theory gives us no guide or proposed way of how to actually get the exact density. So that is why density functional theory is often used in conjunction with Combe-Sham density functional theory. This says, imagine a fictitious system of non-interacting electrons that has exactly the same density as the real system. So a system that has a completely fictitious external potential, that when you insert non-interacting electrons into the system, it just so happens to match the exact density of our real system. And once you have that, then perfect. You have the density, which you can then insert into the functionals. So let's look a bit deeper of how this works. So let's say, for example, we consider a simple 2-electron harmonic oscillator in one dimension. So we'll draw a few things on our graph here, the first being the external potential, which is simply a harmonic oscillator. If we then insert 2 electrons into this well, we get a density that looks like this. And here we've included both of the electrons to have the same spin, so that we have both exchange and correlation effects. If we then, for example, guess that the fictitious system is just the external potential, and we insert non-interacting electrons, we get a different density. This makes sense, as the interacting electrons will have a different density to the non-interacting electrons. Our goal now is to figure out what fictitious external potential gives us the exact density. So what we can do is we can adjust the fictitious potential, solving the non-interacting Schrödinger equation, and as we see, the density changes. And if we have some minimization numerical procedure, we can keep searching over all of these potentials that when we solve the non-interacting Schrödinger equation, we get the same density as the interacting Schrödinger equation with the real potential, like this. So if we insert interacting electrons into the orange external potential, we get the density n. And if we insert non-interacting electrons into the fictitious external potential, the green curve, we get exactly the same density. Therefore, if we insert our fictitious density into our functionals, we get all of the correct observables for our system. So now the problem is, well, how do you determine this fictitious potential? where you don't know the exact density. So this fictitious potential is often called the Combes-Sham potential, and is often chosen to be split into three terms. First, the external potential, which is the potential of our real system, then the Hartree potential, which has been discussed previously, and then plus what is called the Combes-Sham exchange correlation potential, which can be thought of as saying how the potential that is needed to give the exact density despite the fact we have neglected the exchange and correlation effects in this non-interacting picture. So now, this theory again is totally exact. All we need to do is come up with an approximation for the exchange correlation potential, and from this we can compute all of the exact properties of the system. So now, to investigate which of these two formulations, both the self-energy in many-body perturbation theory and the exchange correlation potential in density functional theory, which is the easiest to approximate, we will use the IDEA code, which is the interacting dynamic electron approach. The idea of this is we design a simple 1, 2 or 3 electron model system in one dimension by defining an external potential. As this system is so simple, it is actually possible to compute the exact many-body wave function and density for this sufficiently simple system. We can then compute the exact observables, and then we can also perform approximate methods and compute the approximate observables. And then we can compare these, so we can illustrate why current approximate methods fail, where exactly they go wrong, and how we can improve them. And we have access to many approximations in the code, such as non-interacting electrons, Combes-Sham density functional theory in TDDFT, the Landauer-Bucherer formulation, hybrid functionals, and many-body perturbation theory, such as Hartree-Fock, GW, COSEX, and GW with a self-screening correction. So, the example system we'll look at is a molecule, and the question we will be asking is regarding the structure of molecules. And so, for example, let's say we wanted to know what the interaction between these two atoms were in the molecule, and we wanted to do it exactly with both Combes-Sham DFT and many-body perturbation theory. We could ask which potential is easier to approximate, because if you can approximate the potential well, then the interaction between all of the unbonded atom pairs will be approximated well, and as there are many unbonded atom pairs in this molecule, this would give us a reasonable structure of the molecule. We won't focus on the bonded pairs in this work. And so in order to find out which potential is the easiest to approximate, well, as we're in the, you do this in the idea world to create a simple model of this, and we can look at the exact potential in both cases. And by looking at the exact potential, we can see which looks the simplest, and hence which is the easiest to approximate. So we're focusing on this pair of atoms here. So, let's look at the exact density from Combes-Sham DFT. So we'll model our two-atom pair, unbonded pair, in IDEA by using this external potential in grey, where we just have two different wells. If you solve the exact Schrödinger equation for this system, the density looks as so, with one electron in each well. Again, we are treating the electrons as spinless to make sure our electrons don't form a bond, so that we really are modelling an unbonded pair. If we insert non-interacting electrons into this well, we see that both the electrons occupy the right well. So it is the Coulomb interaction that is lifting the electrons out of lifting one of the electrons out of the right well into the left well. We can compute the exact Combes-Sham potential of this system, and it looks like so, where the right well has been raised by a constant in order to force one of the electrons over into the left well. And we see this looks very difficult to approximate because it has a very strange feature in the centre of the system. We can split this into the Hartree and exchange correlation parts like so. And so we see the Hartree potential shows a Coulomb bump in each well, and the exchange correlation potential cancels the Coulomb bump in each well and adds this step feature in the centre. Now this step feature is extremely difficult to approximate with common approximations to the exchange correlation potential, such as the local density approximation. As the place in the system where this step occurs, the density is essentially zero. So now let's look what self-energy you need to get the exact density from many-body perturbation theory. Now, The self-energy we'll use in this case will actually be the Hartree-Fock self-energy, and that is because in this case, the Hartree-Fock self-energy yields the exact density, and we'll prove this here, because here is the exact density, and then here is the Hartree-Fock density. It's a little hard to see on this graph, so we can illustrate it here. And so, for all intents and purposes, the Hartree-Fock self-energy gives us the exact density in this system, so analysing its features is perfectly good. And so here is the exact self-energy for Hartree-Fock. As you can see, the exchange self-energy in Hartree-Fock depends on x and x prime, and that is what is plotted on the left. It's x versus x prime, where black is 0 and white is -1. So we see that the Hartree-Fock self-energy has no such strange step features. It is simply a smooth feature showing a negative bump at each of the atomic sites. Now, to investigate this a little further, we define the effective potential. Now, the non-local potential in Hartree-Fock, called non-local because it depends on x and x prime, is integrated over an orbital. What this tells us is how any possible orbital could feel a potential due to this self-energy. And so to see what's actually happening, we can define an effective potential. And what this does is it extracts from the self-energy what potential a given orbital is feeling. And the formula is shown in blue there. And so we can do it for our model system. So if we look at just the orbital on the left, we see the electron is on the left, and the Hartree potential it sees looks like so. A Hartree bump on the left and a Hartree bump on the right. So you can see some Coulomb charge on the left and the right side. If we then calculate the effective exchange potential seen by this orbital, it looks like the curve in red, where on the left-hand side of the system, it has negative its own contribution to the Hartree potential, on the right, it's 0. So when we add these together to see the total effective potential seen by the electron, we see it sees the external potential plus a Coulomb charge in the other well, and therefore it stays in the left well. And if we did this for the other orbital, the logic would be exactly the same, but for the opposite. The electron in the right well would see the Coulomb presence of the electron in the left well, and the electron in the left well sees the Coulomb presence of the electron in the right well. This makes perfect sense, and therefore Hartree-Fock gets the correct answer of 1 electron in each well, and it does this simply by having each electron see a different effective potential. But how on earth can this be done in Combe-Sham density functional theory? Because in Combe-Sham density functional theory, as we stated, there is only one fictitious system that all of the electrons see. So how on earth could each electron be put into the correct well without having this nice feature that each electron just sees the other in the other well by this effective potential? And the answer is, well, Combe-Sham DFT has to cancel out the Hartree potential for all of the electrons at once. So as we look at the exchange correlation potential again here, it does what Hartree-Fock does for the left electron, but then it also does it for the right electron at the same time, as every electron has to feel the same potential. Therefore, you end up just cancelling the Hartree potential fully. Therefore, Combe-Sham DFT has no choice but to introduce a very unphysical feature in the fictitious potential at the centre of the system in order to overcome the fact that each of its electrons must feel the same effective potential. And this leads us to the concept of nearsightedness. If we looked at the exact exchange correlation potential for our system, we can show that it's the exact exchange correlation potential of just the left system on its own, so 1 electron in the well, which is just minus the Hartree potential, plus the exact exchange correlation potential of the right electron on its own, which is just minus the Hartree potential, plus a large step feature in the centre. Whereas if we do this for the self-energy that gives the exact density, we can show that the self-energy of the left system on its own plus the self-energy of the right system on its own gives us the self-energy of the full system. This is why we say the system is nearsighted, in the sense that each electron only needs to be concerned with the system close to where it is. It does not need to know in great detail effects of the system at the opposite side of the system. DFT does need this, as each of the systems independently give you totally the wrong answer. You need to include a large step feature that takes account of the physics happening far away from where it is. Therefore, we say that many-body perturbation theory contains advantageous nearsightedness. It is this non-locality that allows the potential that yields the exact density to be much simpler, not needing these unphysical step features. Therefore, you can say this is a conservation of difficulty. The non-local potential in many-body perturbation theory is a complicated object, therefore its features need only be simple, whereas in Combe-Sham DFT, the exchange correlation potential, that is a potential felt by every electron at once, is a very simple quantity, therefore its features must be complicated. So, there is also more information to go in this topic, such as how this relates to the derivative discontinuity and what happens if you include correlation, so the GW approximation, and that is explained in this paper. And so to summarise, today we have spoke about many-body perturbation theory and how it works, and then an alternative, which is density functional theory and how it works, and how these are both in principle exact reformulations of quantum mechanics. But we show that for a given problem, such as an unbonded pair in a molecule, the potential in many-body perturbation theory is actually far easier to approximate. And the potential in Combe-Sham DFT is very difficult to approximate. And this gives us an overarching message that when you're considering a given problem in physics, it is always best to check which formulation you are using is the easiest to approximate for a given computational effort, and so you're not doing unnecessary work. Thank you for listening.